numerator by denominator, what will be the remainder? All the questions will be of the form numerator by denominator, what is the remainder? So there are two cases possible. There are two cases possible. Numerator and denominator are co-prime to each other. Numerator and denominator are co-prime to each other. Are co-prime to each other. Are co-prime to each other. Numerator and denominator. That means HCF of base in numerator, HCF of base in numerator, comma denominator. It is nothing but 1. Two numbers are said to be co-prime to each other if their HCF is 1. Two numbers are said to be co-prime to each other if their HCF is 1. If numerator and denominator are co-prime to each other, there are multiple ways. One is a negative remainder concept. One is a negative remainder concept. And another is an Euler's theorem concept. Euler's theorem. Yesterday we discussed all this. Next one will be Chinese remainder theorem concept. Chinese remainder theorem concept. Next one will be Fermat's theorem concept. Write down in the same way. Write down in the same way. One is a negative remainder concept. Another is an Euler's theorem concept. Chinese remainder theorem concept. And the last one, it is a Fermat's theorem. Last one, it will be Fermat's theorem. When the Fermat's theorem is used, when the denominator, it is a prime number. When the Fermat's theorem will be used, when the denominator, it is a prime number. When the denominator, it is a prime number, Fermat's theorem is used. When the Chinese remainder theorem is used, when the denominator, it is a composite number. When the denominator, it is a composite number. If the denominator, it is a composite number, then the Chinese remainder theorem is used. A prime number is a number which is only divisible by 1 and itself. Which is only divisible by 1 and itself. Chinese remainder theorem is used when the denominator, it is a composite number. A composite number is a number which has got more than two factors. More than two factors. There are three kinds of numbers based on factors. There are three kinds of numbers based on factors. Based on factors, there are three kinds of numbers. Only one factor. Only one factor. If there is only one factor, then the number is called 1. If there are only two factors, if there are only two factors, if there are only two factors, then the number is called a prime number. Then the number is called a prime number. If there are greater than two factors, if there are greater than two factors, then the number is called a composite number. Then the number is called a composite number. Depending upon the number of factors, there are three kinds of numbers. A number which has got exactly one factor. A number which has got exactly one factor. That number is called 1. 1 is a factor for every number. 1 is a factor for every number. Number which has got exactly two factors. The numbers which has got exactly two factors, that is 1 and itself. 1 and itself. Numbers which has got exactly two factors are called prime numbers. A composite number is a number which has got greater than two factors. Numbers which have got greater than two factors are called composite numbers. Numbers which has got exactly two factors are called prime numbers. Only on prime numbers in my paid batch I will discuss 6 to 8 hours class so that a student will understand all the 15 to 18 models of questions that can come in prime numbers. Numbers, the classification of numbers based upon factors. Only one factor, only two factors and greater than two factors. So, negative remainder is used when the denominator can be either a prime number or the denominator, it is a composite number. Negative remainder can be used when the denominator, it is a prime number or the denominator, it is a composite number. Denominator, if it is a composite number, I will use Euler's theorem also. I will use Euler theorem also. Listen carefully to the next few lines, whatever I am saying. If you are unable to solve the problems in less time by using negative remainder concept, if the denominator it is a prime number, then make use of Fermat's theorem. If you are unable to get the answer by using negative remainder concept, when the denominator it is a prime number, use this concept of Fermat's theorem. Step number 2. If you are unable to find the negative remainder concept, when the denominator is composite, go to Euler's theorem. If that is also not giving you the answer, then go to Chinese remainder theorem. Then go to Chinese remainder theorem. This table is of extreme importance to me. If you understand this table, entire reminders chapter will be extremely clear to you. Again, I am repeating this point. If the negative, I will put it in a next slide. All the remainder based problems will be of this type. Either the denominator can be, there are only 3 cases possible. If the denominator it is 1, then it is called a natural number. 4 by 2. 4 by 2 can be optimized as 2 by 1. 6 by 2 can be optimized as 3. 8 by 4 can be optimized as 2. If numerator and denominator are co-prime to each other, if the denominator it is 1, then it is called a natural number. If the denominator it is a prime number. So we are first understanding what are all the cases that can be possible for a denominator. Denominator can be 1. If the denominator is 1, then it is called a natural number. If the denominator can be a prime number, denominator can be a composite number. So 2 cases will arise. What will happen if the denominator is a prime number? What will happen if the denominator it is a composite number? Denominator it is a composite number. See here, sir. Reminder. Slowly, concept by concept, not a single doubt, you will get it in the class. Numerator by denominator. If the denominator, it is a prime number. If the denominator, if it is a prime number, first use negative reminders. If you are able to solve it very quickly by using negative reminder, stop it. If it is taking more time, then go to Fermat's theorem. This is an extremely important slide, sir. If the denominator, if it is a composite number, first try to solve using negative remainder. If it is not giving you answers in shorter time, use Euler's theorem. If it is also failing, then use Chinese remainder theorem. Please put it as very, very important slide, sir. Very, very important slide. This slide will tell you when to use which concept. Very, very important slide. If the denominator it is a prime number, first I will check with the negative remainder. If it is taking more time to solve a question, then we will get into Fermat's theorem. We will solve first by using negative remainder. If it is taking more time, then I will get into Euler's theorem. If it is also taking more time, then I will get into Chinese remainder theorem. Now, yesterday's class, we did this and we also did this. Now we will continue with the next. What is Euler's theorem? Euler's theorem states, Euler theorem is used to find out the remainder when you divide a number by composite number. A power phi of n by n, it is 1, where a and n are co-prime to each other, where a and n are co-prime to each other, and the denominator, it is a composite number. Denominator, it is a composite number. Any composite number can be written as power of prime numbers. P1 power x, P2 power y, P3 power z. So what do you mean by quotient of n? Quotient of n. Quotient of n is nothing but n into 1 minus 1 by P1, 1 minus 1 by P2, 1 minus 1 by P3, 1 by P3. We have seen yesterday this case, and we have done a lot of problems where the denominator, it is a composite number. Where the denominator, it is a composite number. Now see here, we will take up Fermat's theorem. Fermat's theorem. The difference between Fermat's theorem and Euler's theorem is, Fermat's theorem is used when the denominator, it is a prime number. Euler theorem is used when the denominator, it is a composite number. N is a prime number. N is a prime number. If n is a prime number, if n is 11, this can be written as only 11 power 1. If n is 29, this can be written as 29 power n. So the quotient of a n, which is a prime number, quotient of a prime number, it is nothing but, n is nothing but P1 into 1 minus 1 by P1. So any prime number can be written as a singular power of a prime number. 23 can be written as 23 power 1. 31 can be written as 31 power 1. So P1 into 1 minus 1 by P1. These are nothing but P1 minus n. Very, very important point. Please write down. Quotient of a prime number. Quotient of a prime number. It is nothing but prime number minus 1. Prime number minus 1. Take the quotient function of a prime number. Quotient function of a prime number is always given by prime number minus 1. How you got prime number minus 1? Here the n is a composite number. Here the n is a prime number. Any prime number can be written as a singular power. 11 can be written as 11 power 1. 29 can be written as 29 power 1. So P1 can be written as P1 power 1. So it is nothing but P1 into 1 minus 1 by P1. P1 cancel. Answer is nothing but P1 minus 1. P1, it is a prime number. Very, very important key point. So in Fermat's theorem, if n is a prime number, it will become a power p minus 1 divided by p, it is nothing but 1. A power p minus 1 when divided by p, it is nothing but 1. Where p is a prime number. Very, very important concept. The difference between Euler theorem and Fermat's theorem is, Euler theorem is used when the denominator, it is a composite number. If the denominator, it is a composite number, Euler theorem is used. Fermat's theorem is used when the denominator, it is a prime number. If the denominator, it is a prime number, then Fermat, this will become remainder of quotient function of a prime number will become a power p minus 1 divided by p equivalent to 1. A and p are co-prime to each other. P is nothing but a prime number. P is nothing but a prime number. These very, very useful wherever the negative remainder is failing. Examples. First question. Remainder 1. 3 power 6 by 7. 3 power 6 by 7. First check whether the denominator, it is a prime number. 7 is a prime number. 7 minus 1 is 6. So answer for this question is nothing but 1. 23 power 12 divided by 13. 23 power 12 divided by 13. A power p minus 1 divided by p, it is 1. If it is 13, 13 minus 1, it will be 12. It will be 12. I hope the idea it is clear. 9 power 37. 9 power 37 divided by 19. 9 power 37 divided by 19. If you use a negative remainder, 9 square, 9 cube, we have to find out which power of 9 when divided by 19. I will get plus 1 or minus 1. But by using Fermat's theorem, directly you will get the answer. If the denominator it is 19, 19 minus 1, 18. 18 multiple till 37. 18 2s are 36. Remaining 9 power 1 divided by 19. These are nothing but 1. 1 into 9 is nothing but 9. 1 into 9, it is nothing but 9. If the denominator it is p, power of a numerator base, it will be p minus 1. It will be p minus 1. Two more problems. Fourth question. 5 power 57. 5 power 57 divided by 29. 5 power 57 divided by 29. If the denominator it is a prime number, then it will become 2 power 28. 28 2s are 56. Another 1 power of 2 is remaining into 29. So these are nothing but 1. 1 into 2, it is nothing but 2. 1 into 2, it is nothing but 2. 1 into 2, it is 2. One more question. One more question. 7 power 49 divided by 17. 7 power 49 divided by 17. If the denominator it is 17, power should be moving in the cyclicity of 16. 7 power 16 by 17, it is 1. So 7 power 16 power 3 into 7 power 1 divided by 17. Divided by 17. These are nothing but 1. 1 into 7, answer is nothing but 7. 1 into 7, answer is nothing but 7. Very, very important problems. This is popularly called as Fermat's theorem. These popularly called as Fermat's theorem. Reminder 1. A power p minus 1 divided by p, it is 1. Please make a note. Numerator base value and the denominator both should be co-prime to each other. A and p are co-prime to each other. Denominator p, it is a prime number. Fermat's theorem is used when the denominator it is a prime number. I hope the introductory problems on Fermat's theorem, it is clear to you. Next slide, very, very important derivative of Fermat's theorem. We are going to solve it. Pay utmost attention to it. Pay utmost attention. I hope the idea it is clear. Now before that, any introductory problems are there? Fermat's theorem introduction which we have done. This one. Reminder 1. 52 power 30. So a power p minus 1 divided by p, it is nothing but 1. So 31, it is a prime number. So answer is 52 power 30 divided by 31. Answer is nothing but 1 based on the Fermat's theorem application. Already we did the basic introductory problems. 29, it is a prime number. So 28. 28 2s are 56. Another 17 it is remaining. 17 divided by 29, which is nothing but 17. Second question also it is clear. Right. Third question. Before we solve the third question, let me see if I can create some very, very good questions on spot. Questions. 5 power, for example, 5 power 23 divided by 13. 5 power 23 divided by 13. Now, one is in this problem, negative remainder seems to be the best method. Negative remainder directly you can use. 13 means power can be 12. 12 twos are 24. Coming back, doing backtracking, it will be cumbersome. Which power of 5? When divided by 13, I will get plus or minus 1. 12, 11s are 22 into 5 power 1 divided by 13. 25 divided by 13. 13 twos are 26 minus 1. Minus 1 power odd minus 5. Positive remainder, it is nothing but 8. Positive remainder, it is nothing but 8. Very, very easy question. In fact, Fermat's theorem will take little more time. 13 means power is 12. 5 power 24 by 13, it is 1. Question is 5 power 23. So coming back, it will be little cumbersome. So for certain problems where the denominator, it is a prime number, negative remainder seems to be a very, very interesting logic. Very, very interesting logic. Now, for example, if it is 4 power 31 by 17, 4 power 31 by 17, 4 power 31 by 17. Use the same concept as third problem. Which power of 4 when divided by 17? I will get plus 1 or minus 1. 4 square, it is 16. Here directly you are getting it. So this is nothing but 4 square power 15 into 4 power 1 divided by 17. 16 by 17 minus 1. Minus 1 into 4 minus 4. Positive remainder, it is 13. Positive remainder, it is nothing but 13. Positive remainder, it is nothing but 13. Now let us see. Suppose if it is 5 power 31 by 17. 5 power 31 by 17. 4 power 31 divided by 17 can be solved by using negative remainder. 4 square, it is 16. 16 by 17, it is minus 1. Directly you got. 5 square is 25. Remainder is 8. 5 cube, 125. 17 8s are 136. No, it is not giving you. So that is the reason here Fermat's theorem will be helpful. Here Fermat's theorem will be helpful. How the theorem will be helpful? Let us see. We will use yesterday in Euler's theorem. We have seen the backward approach, or most popularly called as backtracking method. Backtracking means you have to determine the known, from that known you have to determine the unknown. 5 power 31 by 17. Because denominator it is 17. Denominator it is 17. Numerator can be 16. So 5 power 16 divided by 17, it is 1. This is according to Fermat's theorem. According to Fermat's theorem. But according to the question, we require 31. According to the question, we require 31. We got 16. What is the multiple of 16 till 31? 16 twos are 32. So it is 5 power 32 divided by 17, which is nothing but 1. 5 power 32 divided by 17, it is nothing but 1. 5 power 32 can be written as 5 into 5 power 31 divided by 17 equivalent to 1. Listen carefully here, sir. From here, very good problem it is there. 5 power 32 we got. But according to the question, we need 5 power 31. So 5 power 32 can be written as 5 into 5 power 31. 5 divided by 17, 5. 5 power 31 divided by 17. I don't know x. When I further divide, answer does not change. Yesterday, the same kind of problem where the power of numerator is less than the quotient function. We used backtracking method. 5 by 17. 17 zeros are 0. Remainder 5. 5 power 31 by 17. We do not know the remainder. That is what we want. If I further divide, remainder does not change. If I further divide, remainder does not change. 5x. When you divide by 17, quotient is nothing but k. Remainder it is 1. Dividend equivalent to divisor into quotient. plus remainder. 5x equivalent to 17k plus 1. So 5x is nothing but 15k plus 2k plus 1. 15k plus 2k plus 1. 15k plus 2k plus 1. These are divisible by 5. These also divisible by 5. 2k plus 1. It is divisible by 5. So k minimum has to be 2. K minimum has to be 2. Why? Because 2k plus 1 equivalent to 5. 2k equivalent to 4. K is 2. K minimum 2. 5x is 35. X value is nothing but 7. X value is nothing but 7. Very, very good question. First we discussed the definition of a Fermat's theorem. Then we discussed how the negative remainder can also be used to get the answer very, very fast. Then we have seen the backtracking method. The notes will be very crystal clear. Each and every models that will come under a Fermat's theorem, everything will be discussed in detail. 5 power 16 divided by 17, it is 1. Multiple of 16 is 32. I want 5 power 31. 5 into 5 power 31 by 17, it is 1. 5 power 31 by 17, it is x. 5x divided by 17, it is 1. 5x is the dividend. 17 is the divisor. Quotient is k. Remainder, it is 1. Dividend equivalent to divisor into quotient plus remainder. 5x equivalent to 17k plus 1. 5x equivalent to 15k plus 2k plus 1. Divisible by 5, divisible by 5. 2k plus 1 should be divisible by 5. K minimum, it is 2. 5x is 35. X is nothing but 7. X is nothing but 7. X is nothing but 7. I hope this fifth problem, it is clear to you. Fifth problem, I hope it is clear to you. Next one. Let us do one more question so that this concept will be extremely clear to you. 11 power, for example, 23. 11 power 23 divided by 13. 11 power 23 divided by 13. Sir, I want to use a backtracking method. You can also use a negative remainder in case if you are getting answer fast by using negative remainder. Please use that logic. 1 minute, sir. Right. Backtracking, let us use. 13 it is there. 13 means power will be 12. So 11 power 12. 11 power 12 divided by 13. It is nothing but 1. A power p minus 1 when divided by p. It is 1. 12 twos are 24. So 11 power 24 divided by 13. It is nothing but 1. I want 23. So these are nothing but 11 into 11 power 23 divided by 13. It is nothing but 1. 11 into 11 power 23 divided by 13. 11 by 13. 13 zeros are 0. 11. 11 power 23 by 13. I want the value. When I further divide, remainder does not change. Remainder does not change. 11x when you divide by 13, quotient is k, remainder 1. So 11x is nothing but 11k. Plus 2k plus 1. 11k plus 2k plus 1. 11k, just 1 minute, sir. 11k plus 2k plus 1. 11k plus 2k plus 1. This is divisible by 11. This is divisible by 11. 2k plus 1 should be divisible by 11. If 2k plus 1, if it is divisible by 11, 2k plus 1, it is divisible by 11. K value, minimum value. You can also take higher values. Further divide, I will get the same answer. K minimum, it is 5. 11x equivalent to 13 5s are 65 plus 1, 66. 66 by 11. Answer for this question is 6. Answer for this question is 6. I hope the idea, it is clear. I hope the idea it is clear. I am seeing the comments. If any valid doubts are there, then I'll discuss. I don't see any doubts in the comments, so we can move forward. We can move forward. I hope it is clear. Right? So this question, I hope it is clear. Next one, sixth question also we discussed.